in ETH in Zurich, who's going to talk to us about the small cancellation theory over Burnside.
Thanks for the introduction, and thanks to the organizers for the invitation to speak here. Can you hear me? I guess you can. Very good. Okay, so I want to talk about small cancellation theory over Burnside groups. This is a joint work with Rémi Coulon. And the goal of this talk is to give you an easy to apply tool for producing infinite periodic groups. So at the end of the talk, each one of you should be able to write down explicitly their new favorite infinite periodic group. So easy to apply. For producing infinite periodic groups. Okay, let me just quickly remind you what a periodic group is. So a group is n-periodic if every one of its elements raised to the nth power becomes the identity. If for all g in the group, we have g to the power n becomes the identity. So here I actually mean n-periodic for some given n. Okay, so let me just tell you a tiny bit of history, which everybody, or many people probably know. So back at the beginning of the 20th century, Burnside asked, if you're given a finitely generated n-periodic group, does it have to be finite? So that's more of a philosophical question. If every element thinks it's finite, is the whole group finite? So is every finitely generated n-periodic group finite? And think about this question. You don't have to study all the n-periodic groups, but you just think about the free objects in classes of n-periodic groups. Let me give you a notation for that. So if S is a set, then the free Burnside group on S of exponent n is given by the presentation. You take S to be a generating set, and you just kill all the nth powers. That's the free Burnside group. Of, well, on the generating set S and of exponent n. And now this question was answered famously by work of Novikov Adyan and by work of Ivanov, saying, well, no, there are infinite finitely generated n-periodic groups, namely if you have at least two generators and n is large enough, then the free Burnside group on S of exponent n is infinite. So this is due to Novikov Adyan. That was 1968 for the case that n is odd. And it was Ivanov who settled the even case, and this took until 1992. So this took quite a while and took a lot of work, quite monumental efforts. Okay, so now we know that we have infinite periodic groups. Now I'm in the fortunate situation that, for example, Damian told you yesterday that there are still interesting questions about infinite finitely generated n-periodic groups. He was talking about non-property T. Also, Jason mentioned that they are interesting from a geometric viewpoint, or they have one interesting feature, they have linear divergence because they satisfy a law. So these are very interesting groups, the n-periodic groups. And now, if we want to study a class of n-periodic groups, we of course need examples of such groups. So how to get examples of infinite n-periodic groups? Okay, and I'm going to give you three answers. One is, well, you just go ahead and understand the proof that they're infinite. When you do that, you're going to look at an infinite presentation of these groups that satisfy some version of small cancellation theory, and you are smart and you weave into this presentation additional relators to get an actual quotient of a Burnside group that has some interesting properties. So first you understand the proof. So that B of S and N is infinite. Then you add suitable relators to an infinite presentation. One example of such a thing is the Tarski monsters of Olshansky. From, I think, 1982. So this is very powerful, but it's very hard. Let me give you another approach. We know, also by work of Olshansky, that if G is a torsion-free hyperbolic group, and if it's non-elementary, then it has some infinite periodic quotient with a bounded period. So then there exists some n such that, let me introduce this notation here, G modulo its n powers is infinite. This was Olshansky 91. In 91, and there's also a version of Gromov and Delzon, which was, I think, 2000 something. Which was later. What's the problem here? The problem here is that you, first of all, you can only get properties of hyperbolic groups in this way, because you can only start with a hyperbolic group, and also the exponent you're killing will depend on the group G you choose. So you cannot use this technique to study an entire class of n-periodic groups. So here, n depends on G. And now let me give you the third approach, which is going to be today's theorem. Which I'm going to give you right away. So that's the main theorem. Of Rémi and myself. It basically tells you that you can just do C prime 1 over 6 small cancellation theory. So the small cancellation theory you first learn when you learn small cancellation theory. So the very classical thing, you can just do that over Burnside groups. So let me give you this precise statement. There exists some magic number n naught such that for all n at least n naught and n is odd, we have, if you have G C prime 1 over 6 presentation, that satisfies three very natural assumptions, which I will give to you in a minute. So we have a C prime 1 over 6 presentation such that we have three very natural assumptions. Then the group, which I want to denote Gn, which is the quotient of the free Burnside group on S of exponent n, modulo the normal closure of the relators, which is of course the same as just the group G modulo its nth powers. Then this group here is infinite. So let me give you the natural assumptions so that you know that this is really a strong result. So first we want that we have at least two generators. We don't want to start it with a cyclic group. And we also want that no relator is S to the plus minus 1 for a generator. So we don't just want to kill a generator. And also we don't want to say that two generators are equal right away. So we don't want to have these relators of length 1 or length 2. Then we also want that no relator is a proper power. What's the point here? We don't want to have torsion in our group to begin with. We don't want to have torsion that would interfere with the torsion we're adding later on. Because if the orders are coprime and things like that, we get into trouble. And the third condition is that no third power is a subword of a relator. Okay, so what's the third power? For example, a to the 3 is a third power, but also ab to the 3 would be a third power. We don't want these as subwords of our relators. Why is that natural? Well, we have our relators in R, but we also have the Burnside relators, which are large powers, and we don't want the two of them to interfere with one another. And I should say right away, the constant 3 I chose here, you can replace by an arbitrary fixed constant, but you're gonna have to adjust your n naught up here. So you can put k up here, you just need to, you're gonna have a different n naught up there. And we have an additional conclusion, which is going to also tell us that some words in the generator are not going to be trivial in the quotient, namely, and whenever W is a proper non-empty subword of a relator, then it does not represent the identity in the group Gn. So, no non-empty proper subword of an element of R represents one, represents the identity in the group Gn. All right. So we know that some words survive, which is going to help distinguishing these groups if we build a couple of them, for example. So this is essentially the baby version of the theorem. We also prove a version of the theorem for the more general graphical small cancellation theory. And we also prove a version for building quotients of free products. Okay.
And S and R can be either infinite or finite sets?
Yes, there is absolutely no restriction at all. All right. So why do we care about C prime 1 6 small cancellation or graphical small cancellation or free product small cancellation? This small cancellation gives lots of examples of hyperbolic groups, of limits of hyperbolic groups with interesting properties. Rob mentioned, for example, the Rips construction you can do in C prime 1 over 6 small cancellation. We have groups with embedded expander graphs that come from graphical small cancellation theory. So these are counterexamples to the Baum-Kahn conjecture with coefficients. Also, free product small cancellation is used for producing undecidability results about certain algorithmic problems in group theory. And with this tool, you can push all these results to n-periodic groups. And I'm going to give you a couple of examples of this in a minute. But first I want to remind you of the definition of C prime 1 over 6 small cancellation and just show you some easy examples that you can actually write down. All right. So the definition. So we take the presentation as R. Then a word U is a piece. Essentially, if it's a common subword of two relators. So if there exists R not equal to R prime, cyclic conjugates of elements of R union R inverse, such that we can write R as UV and R prime as UV prime. So U is an initial common subword of these two relators. This triple equality here just means reduced without cancellation here. And the small cancellation condition tells you that if you have a common subword of two relators, this is going to have to be short. So we say the presentation satisfies C prime lambda if whenever a piece U is subword of a relator, so subword of a cyclic conjugate of R in the set of relators, then the length of U is strictly less than lambda times the length of R. And we also want the technical assumption that all the relators are cyclically reduced, so that we are actually computing the right length here. Okay, what does this mean geometrically? What you should think of is, you should think of your Cayley graph. This Cayley graph has embedded cycle graphs that correspond to your relator. So it has cycles that are labeled by the relator. So you can read the relator on a closed path here. Say this is R and this is R prime. And if they have some overlap, then this overlap is labeled by a common subword. So the condition tells you these overlaps are short. All right. So examples. So the example 0 is that got this whole thing started, the whole theory. It's the presentation of a surface group of genus 2. Let's just product of two commutators. It's easier to think about cycles labeled by relators, so let's just draw the cycle. So that's A, B, A inverse, B inverse, C, D, C inverse, D inverse. Now, how do we find out about pieces in this presentation? Well, we just look at all the cyclic conjugates and their inverses of these relators, and we look at common initial subwords. So, for example, the common initial subword A, we see in this, of course, the relator we've written down, and the cyclic conjugate of the inverse that we get by reading the relator from here in the different directions. So that's A, B inverse, A inverse, D, C, D inverse, C inverse, B. And you see, OA is a common initial subword of two relators. So it's a piece. But you're going to notice AB is not a piece, because here we have AB and here we have AB inverse. So you will see that all the pieces for this presentation here have length 1. Another way to think of this is when you look at the Cayley graph of the group, you see it's an octagonal tessellation of the hyperbolic plane, which is covered by these cycle graphs here, and any two overlap in just one edge. So the pieces have length 1. So this satisfies C prime 1 over 8 plus epsilon for every epsilon, because the relator here has length epsilon and we require strict inequality. So this is satisfied. So in particular, C prime 1 over 6 is satisfied here. Let me give you a more interesting example. So we call that example 1. So we take 3 generators, A, B, and T, and we just let xi be words in A and B of length I. Okay? So we have the length of xi is I. Let me tell you how to get a small cancellation presentation here. We just write down the first relator is tx1, tx2, and so on, tx100. Second relator is tx101, tx102, and so on to tx200. And you go on and you get an infinite family of relators like that. What's the point here? So that's right. Sort of R is R1, R2, and so on. What's the point here? If you look for pieces in these relators, you're going to notice that no piece contains 2 t's, because the spacing between 2 t's is always unique. There's one place where they are 100 apart, one place where they are 1 apart, one place where they are 2 apart, and this is distinct everywhere. So no piece has 2 t's. And then you can check that this also satisfies C prime 1 over 6. Probably something stronger, but you would have to do a computation there, and let's not do that now. Okay. So that's how you get an infinite C prime 1 6 presentation. Now let me show you how this lets you get an infinite C prime 1 over 6 presentation that satisfies the assumptions of the theorem here. And we're going to use that to produce uncountably many n-periodic groups. Just as an easy example. So we need some words without third powers. How do we get that? We study literature and we find a nice sequence which is called the Thue-Morse sequence. So this is example 1 plus. So this is going to be built on the Thue-Morse sequence. And I should say that we used this example for other purposes in a joint work with Gulnara Ashantseva, Chris Cashin, and David Hume. So that's Ashantseva, Cashin, G, Hume. How does that work? Well, we write down an infinite word, which we produce in the following way. We put some initial subword, so x infinity is going to be an infinite word in A and B. How does it work? We write down x infinity, it starts out with an A. What do we do next? We exchange A and B and A in the initial subword, which in this case we exchange A for B, and we append what we get. Okay? So what's the next step? Now we have initial subword AB, so we exchange A for B, we exchange B for A, and we append this here. So this is ABBA. Now what do we get if we flip ABBA? We get BAB. So we append this here, and we keep going like that to get an infinite word. Now the main feature of this word is, or the interesting feature for us, this has no third powers as subwords. Okay? So we can use this to build a presentation as in the theorem. How do we do that? We write, this is going to be a definition of the xi we had above. We write x infinity is a product x1, x2, x3, and so on, with the length of xi should be I. So x1 is A, so x1 is A, x2 is BB, x3 is ABA, and we go on. And now we just apply the above construction. So we construct the set of Ri for I in the natural numbers as above. And you're going to notice that the t's we introduce do not give additional powers. So we have a presentation. This is going to be R as in the theorem. So we get an infinite periodic group. So for n large enough odd, we get that the quotient of the free Burnside group by R, this is infinite. Okay, so that's one new n-periodic group. We can also build just uncountably many right away. We take, for any subset of the natural numbers, we let the set R of I be just the set of all relators R little I that have their index in the index set I. This is going to give us uncountably many presentations, and you have to do a tiny bit more work to see that this actually gives you uncountably many pairwise non-isomorphic n-periodic groups. Pairwise non-isomorphic n-periodic groups. Okay, and I should say it was known that there are uncountably many pairwise non-isomorphic n-periodic groups before, but this is just a very easy construction you can get without theorem. Okay, so these were some examples. Now let me give you some new results we get without theorem. This is what we call applications. Theorem. This is going to use the graphical version of the main theorem. It says there exist n-periodic, finitely generated n-periodic groups with coarsely embedded expander graphs. So this was first suggested in existence of such groups was suggested in a paper of Archancev and Delzant, and we get a proof for this. So we have n-periodic counterexamples for the Baum-Cohen conjecture with coefficients, for example. And I should say for the experts here, we know that they're coarsely embedded. We don't know that they're isometrically embedded. We conjecture, but it's not clear. And let me give you another result, which is about unsolvability of certain algorithmic problems. Namely, well, first I need a notation. So what it means to be finitely presented for an n-periodic group, namely an n-periodic group G is relatively finitely presented if there exists some finite generating set and some finite set of relators, so some subset of the free group 1S with R finite, such that we can write G as the quotient of the free Burnside group on S of exponent n by the normal subgroup, by the subgroup normally generated by R. Okay? I mean, that's one of the open questions about periodic groups and periodic groups. It's unknown if there is a finitely presented infinite n-periodic group. Not relatively finitely presented, actually finitely presented. So this is the realm we can play around in. And now the theorem we get is, well, for finitely presented groups, it's known as the Adyan-Rabin theorem. And we get this theorem in the category of n-periodic groups. And it basically says that most of the reasonable properties of groups are undecidable from a finite presentation. What's the result? So, theorem CG. There exists our magic number, n naught in the naturals, such that for all n, at least n naught odd, and not prime, I'm going to comment on this in a minute, we have suppose P is a property of groups such that there exists an n-periodic group that has the property and, n-periodic and relatively finitely presented. Relatively finitely presented that has the property, and there exists an n-periodic relatively finitely presented group that there exists such a group. Well, we call the group that has the property, call it A. And we also want the group B such that any group containing B does not have the property, so B is a bad group. Then the conclusion is there does not exist an algorithm that just takes a finite relative presentation of an n-periodic group and decides if the group has the property or not. Takes a relative finite presentation of an n-periodic group G G is input and decides if G has P or not. So what sort of properties can you plug into this theorem? For example, triviality. trivial group is n-periodic. Let me just write down a couple of examples. Triviality, finiteness, being cyclic, being abelian, being nilpotent, being solvable, being amenable. For example. So this is a very efficient theorem. It gives a lot of results very quickly. Let me mention how the proof goes. The proof takes an n-periodic group with unsolvable word problem, which is where we need the assumption that n is not a prime, because Olga Kalampovich constructed an n-periodic group with unsolvable word problem under the assumption that n is not prime. And we use a version of graphical, a free product small cancellation theory to promote the unsolvability of the word problem to the unsolvability of this question here. Okay. So the proof of this theorem from our main theorem and from Olga's result is less than a page, for example.
We need a generalization of Rabin's theorem or not?
We don't use his.
Because in the original theorem of finite presentation, but you have related finite presentation.
Yes, but we just apply
The argument.
we modify the argument. This argument, I think, goes over H&N extension. We transpose it to free products.
You have a generalized version of the theorem also. Somehow.
A different version, yes. Not going through H&N, but going through free product, yes. And then we apply what we like to call the Burnsideification. We kill the nth powers. All right. Good. So I gave you a nice theorem. I hope I convinced you it's nice. I gave you some applications. So I also want to talk about how we prove this. So when I first gave a talk about this, I was asked, well, why did people not notice this nice result? I mean, people have been studying Burnside groups since the beginning of the 20th century. People have been doing C'(1)6 small cancellation at least since the 60s. Why did nobody write this down, or nobody find this, or nobody even suspect this, I guess? And you're going to see in the strategy of proof that we use some very modern techniques in what we do. Okay. So, how to prove? So, what we want is we want to take our free Burnside group of exponent n, and we want to get that we can build some quotient that's infinite. So we want to find out what happens here. And we want to do small cancellation theory. Now, small cancellation theory is good at producing quotients of groups that have some interesting actions on hyperbolic spaces. This here is a group where every element has finite order. This is never going to have a nice action on a hyperbolic space. There cannot be a loxodromic. So what we do is we take a different route. We don't start it with the free Burnside group, but we actually started with the free group. Free group is nice. It acts on a hyperbolic space. It acts on a tree. And we first take the quotient of the free group by our small cancellation relators R. And then we apply some new results. Let's say that these groups here, which I call this here G, and this Gn in the main theorem, we apply some new results that say that these groups admit some nice actions on a hyperbolic space. And then we're going to apply some results of Rémi that say that if you have a nice action on a hyperbolic space, then you can build a periodic quotient. Okay? So what did I want to say? The free group on S acts on a tree. We can build infinite quotients. G, and then we use that G acts on a hyperbolic space. This is a result of Alex Sisto and myself from 2014. And then we use that you can build infinite periodic quotients. And this here is essentially a result of Coulon from 2013. All right. Yeah, I mean, the fact that we have to go this roundabout way may suggest that there's a different way of thinking of small cancellation theory, that you shouldn't always think of acting on a hyperbolic space, because you can do it for a Burnside group. But yeah, that's not the way we can prove things, at least. Okay. So we call this periodic quotients. Of groups acting on hyperbolic spaces. And when I say acting, I want acting in a nice way. And we've learned at this conference that the nice way is to be acylindrical. So let me just remind you of the definition here. Group G acts on a space X, which we want to be delta hyperbolic. Then the action is well, we have three numbers here, L, N, and epsilon acylindrical. Well, we have some, David called it a uniform properness for pairs of points that are far away from each other. So for all x and y in X, with the distance of x and y at least L, we have that the number of G's G in the group that almost fix X. So d of x and gx is less than epsilon. G should also fix y almost. D of y and gy is less, or is at most epsilon. The quantity of these elements should be at most n. Sorry. Okay. So the picture you have in mind is you look at any pair of points that's far away, x and y. Here they're far away, distance L. And you want to look at the g's that move both x by little and y by little. Okay. And yes, let's continue here. The point is that if you have a group that acts acylindrically on a hyperbolic space, then we can build a periodic quotient. So it's essentially the theorem of Coulon. We slightly adapted the statement, so the statement you're going to find in our paper, which is you fix your constants L, N, and delta. Then there exists a magic number, N naught, such that for all n at least n naught odd, we have the following statement. If we have let G be a torsion-free group. G should act on a delta hyperbolic space. Delta hyperbolic space. We want the space to be non-elementary. We want it to be interesting. So we want, say, the boundary has at least 3 points. Such that there are no elliptics, no non-trivial elliptics. Then Gn, which is G modulus nth powers is infinite. And you also have some control on the injectivity radius of the map from G to Gn, namely G to Gn is injective on the ball of radius 3 in the X pseudometric. So the metric on G you get induced from the action on X. And here again the constant 3, as before, is arbitrary. You can replace this by any other constant, but you're going to have to adjust your n naught up here. Okay, what's the point here? Yeah?
Eccentricity is missing from
Did I?
Haven't used L.
Oh, I'm sorry. Yes. Of course, we want the action to be, I'm sorry, to be acylindrical with these constants here. So the action of G on X is L, N, and 100 delta acylindrical. Yep, thanks for the comment. Okay, so what's the point? We have an acylindrical action in a hyperbolic space. We have no elliptics, which means all the elements are loxodromic. Now, François, for example, explained to us that we can understand the normal closure of a large power of a loxodromic. We know what that looks like, more or less. What Rémi tells us is that we can actually understand the normal closure of large powers of all the loxodromics simultaneously. Okay. And this is why this works. Okay? And now I want to tell you why we can apply this to small cancellation groups. Let me start out with a folklore result that sort of captures the initial idea of small cancellation theory, or at least in a modern interpretation. Namely, if you have a finite C'(6) presentation, then the group, or the Cayley graph of the group, is hyperbolic. And you also know that some words are non-trivial in your group, namely, well, let me phrase it like this: any cycle labeled by a relator is an isometrically embedded cycle graph. Okay, what's the picture you should have in mind? You should think of your Cayley graph like in the surface group picture as covered by your relators and they have pairwise small overlap. Let me attempt a picture here. So these are going to be heptagons, which have reasonably small pairwise overlap. Okay, so you should think of your Cayley graph. You should think of this going out to be a tessellation of the hyperbolic plane. You can think of your Cayley graph as being covered of these cycles labeled by relators with pairwise small overlap. So relators have small overlap. And hence you have a linear isoperimetric inequality, and hence you have hyperbolicity. Okay, now this is for a finite presentation. What happens if you have an infinite presentation? Well, you have your Cayley graph covered by larger and larger isometrically embedded cycles. Isometrically embedded cycles are very fat triangles, so you're going to break hyperbolicity. Now, I have more blackboard space, very good. What Alessandro Sisto and I realized in 2014 is that these larger and larger embedded cycles are really the only obstruction to hyperbolicity. And the statement is there exists delta such that whenever you take a C prime on 6 presentation, and W, the subset of G, that's all subwords of elements of R. Then, if you add this set W to your generators, so the Cayley graph of S with respect to S and W is delta hyperbolic. What's the picture? Remember, this is a cycle labeled by a relator. You add a generator for every subword of a relator, meaning you connect any two vertices on this cycle. So you attach a complete graph. So if you will, you perform a very strong coning off of all the relators, each one of the relators. And what we figured out is that this gives actually hyperbolicity, and in a uniform way. So the delta is uniform. It does not depend at all on which particular presentation you chose. Yes, the way we proved that in the end was we took a nice result of Bowditch that tells you that if you have an infinite presentation that has a linear Dehn function such that all the cycle graphs in your Cayley graph that are labeled by relators, if all these cycle graphs have uniformly bounded diameter, then the Cayley graph actually is hyperbolic. And this here gives us uniformly bounded diameter for all the cycle graphs.
Does it depend on anything? Does it depend on the size of S? For example?
Nothing.
So what is it?
10 roughly. Depends on which definition of delta you want, but
Yeah, for one of them, it's what?
I think it's 10. 10 is an upper bound at least. Oh yeah, and also if G is as in the main theorem, meaning that it's not virtually cyclic is what we need here, then the space we get, we call it X because X is a good space, is non-elementary. So it has at least 3 boundary points.
Bigger than or equal to 3.
Yes, thank you for that. I mean, we use this to show that these groups are acylindrically hyperbolic. but that's not the point here. The point here is a different theorem, which Rémi and I proved, and which also independently, with different motivation, Caroline Abbott and David Hume proved, that says, suppose no k plus first power is a subword. So, first you fix some k, let k be a number. Suppose no k plus first power is a subword of a relator. Then there exists a constant n, which only constant n, which only depends on k. So n is n of k, and L, which is L of k. So again, independent of the presentation, such that G acting on x is as acylindric as we wanted, namely L n 100 delta acylindrical. Okay? How do we do that? We understand pretty well what the Cayley graph, just a normal Cayley graph of a small cancellation group looks like. It's built from relators with small overlap that are glued together. But what we are studying here is the metric in the Gromov space, where you have all these red shortcuts. So what you need to show is that the geodesics in the Gromov are actually very close to the geodesics in the original Cayley graph, and then you use this interplay to prove acylindricity of the action. Okay? Good. So, we need to patch things together. We have our acylindrical action. Well, in the theorem I stated we chose k equal to 2. So we get the infinite periodic quotient. Let me also show you how you get the non-triviality of these group elements. So I told you that the result up there gives us injectivity on a small ball in the space, right? Radius 3. Well, what's the space here? We cone off all the relators, meaning that every subword of a relator has length 1. So this small ball, I mean, it's not small after all, but all these subwords of relators have length 1 in this space. So the injectivity ensures that they're not killed by the quotient map. All right. And I want to say a word on the powers condition, where it comes into play geometrically. Because in the statement of the theorem, when you look at Burnside groups, it's very natural that you want to assume something on your powers. But then you translate everything into an acylindrical action, and there the question is, why would you want to care about powers there? And so the reason is the following. So the powers condition. The observation is, if W to the K is subword of a relator, then its translation length for the axis, for the action on X, so the translation length of W, is at most 1 over K. Because W to the K translates by 1. It's a subword of a relator. So if you have the kth power, the translation length can be at most 1 over K. So suppose arbitrarily large powers occur as subwords. Then one of the following holds. Well, if the same power of one word appears over and over, then it doesn't have positive translation length, so it has translation length 0, so it's an elliptic. So there exists a non-trivial but then we cannot apply the theorem. We cannot handle elliptics. So we need to rule out this case. What's the other case? We have powers of different words. But then the translation lengths are not bounded away from 0. This is if you have powers of different words. So this cannot happen if you have an acylindrical action. In an acylindrical action, the translation lengths are always bounded away from 0. So this powers condition really has a geometric interpretation that we need to do what we want. Okay, I think I'll stop here. Thank you.
Dominik, a nice lecture. Any questions? Yeah. We'll start back then.
Yeah, if you, instead of just starting out with one of these free Burnside groups, you start off with a free Burnside group and the free product of some free group, you reckon you can get a similar kind of theorem?
Let me think. Yes, you should be able to match this up. So make a mix between free product small cancellation and regular small cancellation. This should work.
Yeah, if you don't take any relators at all, I mean, are you getting a different proof that the Burnside groups are infinite, or is that is that Rémi Coulon's proof, or is that an old?
That's Rémi Coulon's proof essentially.
Oh, so he had a new proof.
Well,
that
he,
Burnside groups were infinite. Yeah.
I think what he did was he gave a new proof of the Gromov version that free Burnside groups are infinite. And this result here is a generalization of this. Yes. Yeah?
How does your construction or variation of this Eden-Rabin theorem work? What do you actually, how do you build that? I mean, you do a different construction there to.
So what you do is you take your you take this group that has unsolvable word problem. You write out all the words in the generators of this group, and you cannot decide if these represent the identity or not. And then you build test groups using free product small cancellation, such that the group has the property or not if and only if the word is trivial or not.
Yes, sir. How's this test group built from the present? That's what I'm asking. What does it? I mean, is it?
You take a free product and then you kill a couple of words. Basically, you say that all the generators of the group are killed if and only if this word is the identity. It's a finite free product small cancellation presentation.
Anything else? Well, let's thank Dominik again. Go to lunch.